Welcome to The Explainer. Today, we're taking a deep dive into something that honestly often feels like a bit of a black box, the mechanical assembly line of large language models. If you've ever watched a paragraph of text just magically appear on your screen and wondered what exactly is happening under the hood, well, you're in the right place. We're going to strip away the magic today and look at the actual machinery together. Okay, let's dive into this. Here is our factory tour map for today. We'll start with the magic of inference, then break down the two-phase generation process. After that, we'll look at exactly how these models choose the perfect word. And finally, we'll wrap up with speed, memory, and optimization.
All right, Section 1, the magic of inference. Let's get the basics down.
So, the million-dollar question, how does an LLM actually write? Now, you might be wondering this yourself. When you type a prompt into a model, there obviously isn't a tiny writer inside drafting a response. To really understand how these models work, we first have to completely throw out the idea that AI writes the way you or I do. It doesn't form a complete thought before the pen hits the paper. Not at all. Instead, it all comes down to inference. Inference is basically the process of using a trained model to generate text by leveraging its learned probabilities to predict the very next token. That is literally it. It is a strictly sequential generation process. It leverages billions of parameters to formulate responses exactly one word or token at a time. Think of it as a highly advanced version of autocomplete.
And this brilliantly illustrates how they pull it off. The attention mechanism. Take a simple sentence like, the capital of France is. When the model predicts the next word, it knows that not every word in that sentence carries equal weight. To figure out that the next word should be Paris, it heavily focuses its attention on capital and France, while pretty much ignoring the words the and is. This attention mechanism is the absolute game changer that sets modern LLMs apart from the early language models.
But you know, an LLM's attention span isn't infinite. This working memory, which we call context length, is strictly limited by a few really practical factors. We're talking about the model's actual architecture and size, the available computational resources, and just the sheer complexity of your input. In an ideal world, sure, we'd feed the model an unlimited amount of context, but hardware constraints make that incredibly expensive and just completely impractical.
Moving right along to Section 2, the two-phase generation process. Let's look at prefill and decode.
So, text generation actually happens in two distinct phases. First is the prefill phase. Think of this like the prep cooking in a busy kitchen. It processes all of your input tokens at once. Then you have the decode phase. This is the actual cooking. It's generating text autoregressively, just one single token at a time. The crucial thing to grasp here is that the heavy lifting actually happens up front, way before the lightning-fast manufacturing of new words even starts.
Let's look a bit closer at that heavy lifting in the prefill phase, because before a model can write, it has to read. It first tokenizes your input into basic building blocks. Then it converts those blocks into embeddings, which are essentially just numerical representations of what those words mean. Finally, it runs those embeddings through its neural networks to create a rich, deep understanding of your context. This is incredibly computationally intensive. It's basically reading and comprehending the entire recipe before it even turns on the stove.
Okay, let's move to the decode phase and see how this builds. Once the prep is done, the model enters this phase and uses a four-step loop for every single new word it writes. It computes attention by looking back at the context, calculates the probability of what word should come next, selects that token, and then decides if it should stop or keep going. And because it has to keep track of all the previously generated tokens every single time it does this, this phase is incredibly memory intensive.
All right, Section 3, choosing the perfect word. Let's talk about sampling strategies.
So to control that exact moment of creation, we use these things called sampling strategies. The model starts with raw logits. Think of logits as the model's initial gut feelings about the next word. But then we can apply temperature, which is literally a creativity dial. Crank the temperature up past 1, and the model gets more random and creative. Turn it down, and it gets highly focused. We also use tools like top P and top K filtering. These restrict the model so it only considers the absolute most likely words, which is how we ensure the text actually makes sense.
But what happens when the model starts sounding like a broken record? You've probably seen that happen, right? Well, we fix that with penalties. We have the presence penalty, which is a flat, fixed penalty applied if a word has been used before. This really encourages new vocabulary. And then there's the frequency penalty. This one is a scaling penalty. It gets harsher and harsher the more times a specific word is repeated. These act as gentle nudges early in the token selection process to keep the output fresh and engaging.
And, just like a good story needs proper pacing, we absolutely have to tell the model when to shut up. We control these boundaries using token limits or stop sequences, like telling it to stop whenever it generates 2 line breaks. Or we just let the model naturally output an end of sequence, or EOS token. This ensures our outputs are the perfect size for whatever we need, whether that's a quick, punchy tweet or a massive 1,000-word essay.
Now, what's really interesting about this next concept is that it's a completely different approach. It's called beam search. While everything we just discussed makes decisions one single token at a time, beam search explores multiple possible paths simultaneously. Think of it like a master chess player thinking 5 to 10 moves ahead. It calculates the probabilities for multiple sequences at once and chooses the highest overall path. Sure, it requires way more compute power, but it produces incredibly coherent, grammatically flawless text. Which brings us to our final stop, Section 4, Speed, Memory, and Optimization. Let's look at the real-world challenges.
If you are the one managing this factory, there are 4 metrics that completely dictate your life. Think of time to first token, or TTFT, like how fast a customer gets their appetizer. Time per output token, TPOT, is the speed the rest of the meal arrives. Throughput measures how many tables you can serve at the exact same time, and VRAM usage is essentially the physical size of your kitchen, like how much GPU memory you actually need. And let me tell you, that last one is almost always the primary bottleneck in real-world applications.
And VRAM usage brings us right to the context length challenge. You see, memory usage grows quadratically with context length, while your processing speed decreases linearly. We have these incredible recent models now, like Qwen 2.5 1 million, that can process a massive 1 million token window. But processing that much context, that demands a severe and incredibly careful balancing act between your available VRAM and your processing speed.
So the crucial point is, how do we actually make long context possible without our servers literally catching fire? The answer is KV cache optimization. KV caching massively improves speed by storing and reusing intermediate calculations. Rather than forcing the model to do the exact same complex math over and over again for every single token, we just cache those calculations in memory. Yes, it uses more RAM, but it saves immense, game-changing amounts of time. Which leaves us with this final thought for today. We've seen how the inference factory works, how tokens are chosen, and how caching lets us expand that working memory. But as these context windows continue to expand and optimization techniques just keep getting sharper, what new human-like capabilities will emerge when an LLM can flawlessly remember everything you have ever told it in a single prompt? The field of inference is evolving at blinding speed, and I really hope this explainer has given you the foundational lens to watch it all unfold. Thank you so much for learning with me today, and keep exploring.